So, this week we're going to talk about thunderstorms. So, what do we need to form a thunderstorm? Obviously, the air has to be unstable. We've got to get it to rise real well. So, we've talked about that in the last couple of chapters now. Hopefully, you're getting a little bit of an idea of how an air parcel can become unstable and start going up. This is Saturday, so you guys in Ohio are getting severe thunderstorms today, or at least you have a severe thunderstorm watch in part of the state. And it may be expanded further east, it looks like, later. So I thought I would go more with that, but I wanted to give you a brief look at thunderstorms. Thunderstorms really, they only last about an hour in most times. Why? That is one individual thunderstorm cell. So say it's summertime, and you have this parcel of air rising up, as you can see on the left. It becomes unstable, continues to rise. And maybe it's fairly unstable and really rises to great height, maybe 40, 50,000 feet up. Well, notice that the first stage is just all rising air. It actually isn't much rain during that stage, towering cumulus stage. In the mature stage, you begin to get a downdraft on one side of the front storm, usually towards the back side of it. And what happens here is you've got so much moisture in the air that even though there's an updraft there, the rain droplets are getting so big that they begin to go down. And when they do, they actually pull the air down. That air that's sinking, those raindrops that are falling, actually begin to evaporate some as they drop. That's cooling. It makes that air more stable, so it tends to go down. That's why when it starts raining in a thunderstorm, it's cooler than out ahead of that thunderstorm, typically. Well, as rain-cooled air comes down to the ground, and you'll notice when it hits the ground, it can't go into the ground, so that air spreads out towards the front of the thunderstorm and towards the back of the thunderstorm. And eventually, that air moves out so far in front of the thunderstorm that it's all rain-cooled. It can't find any of the moisture, warm, humid air it used to have to help those air parcels rise. The thunderstorm dies, and that's the dissipating phase. So, with that, we also have thunderstorms clusters. So, we just looked at one single cell. Now, sometimes thunderstorms can group in multi-cell clusters or even multi-cell line. And eventually, some thunderstorms make supercell. One of the interesting things here is every one of those, which phase thunderstorms work into is pretty much based on wind shear. So the more wind shear, the better chance you can go from a single cell to a multi-cell or to a line, and then even more wind shear is required for a supercell. And oh yeah, you need a lot of instability as well. So here you can see a multi-cell cluster. You have one individual cell developing at the southern end of the line. It grows as it transitions through the line, as this line is moving to the east, and eventually dissipates on the northern side of the line. So typically the strongest cells are in the southern side of the line. And one of the things I wanted to talk about with thunderstorms is more thunderstorms occur in the south. You can see the number of thunderstorms days here. But notice Florida. Why in the heck does Florida get so many thunderstorms? Well, they're well down south. They're surrounded by warm, moist water, obviously moist water, and they wind up with sea breezes on both coasts. So you wind up getting lift, causes the thunderstorms to develop. Oh yeah, but if you looked out, you would think, oh, the same thing would be happening in Hawaii. But no, Hawaii actually has a trade wind inversion. We talked about it last week some. That inversion keeps the clouds from getting too tall. Yes, it can rain a lot in some areas of Hawaii, but they do not get many thunderstorms because of that trade wind inversion. So wind shear is what enhances these thunderstorms. And one of the things also with this is, one of the questions you're going to get is, what is a pattern that causes, a synoptic weather pattern that causes severe weather in the Midwest? And here in the Midwest we're talking about is Texas, Oklahoma, Nebraska, and Kansas. And that is Tornado Alley in the literally where they mostly form a lot of times. So what happens is you get a strong low that develops, probably over Kansas. With it, you have very strong tropospheric jet, your jet stream that helps to develop that low. You have the divergence there. This pulls in strong continental polar air. Ahead of that, your winds are southerly. They're pulling in a lot of maritime tropical air. Oh yeah, you have a desert down here, so you can pull in some very dry air. So what you wind up with is a warm front here, that strong, very tropical, very high level jet causing the divergence aloft, and a very strong low level jet bringing all this moist, humid air out of the Gulf of Mexico and up. Notice the wind shear here. If you were to send a balloon up, it would start moving to the north. At some point, if it got higher, it's going to start moving to the northeast and maybe even due east. So that is a lot of wind shear. There's a lot of wind increase and there's a lot of wind shear. That is why it's very favorable for these extreme thunderstorms and supercells to develop. So let's take a look at some of this a second and what is really going on right now. So here is what the Storm Prediction Center in Norman, Oklahoma says. You have a severe thunderstorm watch out for this area. Notice this cluster of thunderstorms has been moving along for a while. It even continues to form thunderstorms on the southwest side of it as it's moving. So why is that there? That's really the key to this whole question. So let's take a look at what's happening real time. Notice lots of outflow out ahead of it. Very nice line of lightning here along this. Interesting to me, one of the things I'm seeing is I would look at this area for having potential for flash flooding later on, because you're getting more and more thunderstorms back in here that are going to go over the same area. This is a cluster of thunderstorms or mesoscale convective system. But if we were to look back in time, maybe I can get a few more images here. And we'll try to see if we can get a better shot at just where this really developed at. Because it's been around for a little while now, obviously. And of course, it takes a minute to load up here, but once it does, we should be able to get a look back how far back west this actually began to form. But in the meantime, while it's loading, let's take a look at this. What's it forming on? It's forming on a stationary front. It's on the north side of it. And that is where it's forming and moving down. There's another cold front up here coming. Remember yesterday, on Thursday, we talked about a cold front coming through your area. Well, that became stationary, and right here is where that boundary is. It lines up pretty well with those thunderstorms. And it looks like they actually formed literally over the area where the boundary began with the other cold front coming in. So they're moving with that direction here. So they actually formed back over Illinois, Indiana, overnight. Interestingly, when you look at an upper air sounding sometimes to see, this is Wilmington, Ohio, or near Dayton. This is the morning upper air sounding. Temperatures are in red, green, dew points. All that's plotted. Oh yeah, one of the interesting things with meteorologists like to do is we like to plot temperatures that go -10 went this way, -20 goes this way. So we plot the temperatures slanting to the right, and we compress. Since the atmosphere is compressed, notice the 1,000 to 850, 850 to 700, all of a sudden a little further, 700 to 500, significantly more. But we push all these lower levels, the compressed atmosphere, down a little lower. This morning you can see temperatures are fairly cool, relatively cool, 70-some degrees. But it's actually warmer a little bit aloft. Right there is your convective condensation level. If you were able to lift a parcel of air from down here up, it's going to form clouds right around 850 millibars, probably about 3,000 feet up. And if you do that and lift it up, moist adiabatic lapse rate is right here. That's the actual temperature of the air parcel compared to the temperature of the surrounding environment. Notice the separation. That's a lot. So if you can get these air parcels to rise in Ohio today, it's going to be very unstable. And because you already have thunderstorms, you have an old front, that's why they're rising so much. The Storm Prediction Center also loves to have a whole bunch of look at different things to see what's going on in the weather. And this is a moisture convergence. Moisture convergence is a fabulous way to predict where thunderstorms might develop in the future. And if they're ongoing, you want to see this continue to increase and grow out ahead of the storms. And we can see here there's a nice area of moisture convergence right in here. What that means is the air is converging, but it's also pulling in a lot of moisture right there. We know that surface air converging is going to rise, so we're actually causing a lift in the atmosphere right in this area and back along here. So that is where the thunderstorms are going to continue to develop. We can also look and see how the surface map looks at this time. And really not much in the way of low pressure that you see. There's a weak cool system here where these thunderstorms are because of the uplift and all, but nothing impressive. Actually, the lower pressure back in here and high pressure out ahead of it. But notice the winds are turning into this system right in here. So these winds are all moving in, helping to maintain this circulation. Well, if you wanted to look at wind shear with this, we talk about effective wind shear from surface to 6 kilometers. And if you're looking for severe weather, you generally want 35, 40 knots of wind shear. Well, what you're seeing here is 35 to 40 knots. Here's some 50 knots wind shear just to the west of it. So it's actually borderline severe. It's having a hard time really being really major severe outbreak because of that. But with enough shear here, it could continue propagating across Ohio, and maybe some of these winds out to the west will work into this system during the day. Keep it going. You may have some more wind shear there to keep. Another interesting thing is just looking at how much CAPE is convective available potential energy there is with this system. Notice right in here is the maximum area. It's right out ahead of it. It's over 2,000 joules per kilogram squared, if you're interested what the units are. But this is the area that you would expect this strong lift to take place, because that's where it's most unstable. Oh yeah, back in here, there's another whole area that's developing. Very unstable air and all. So there actually will be some more thunderstorm complexes developed out here along that area as well today. So just looking at all of this, that's why they have this box out. If you go back on this, you can see there's an enhanced area here for severe weather today, and we noticed the CAPE were pretty high back in here. So there may be complex. Here's another one coming into this area right now, severe. So there may be several watches up today with this convection up in here. So I hope you got a little bit out of this severe weather, out of understanding how thunderstorms work. They're a very interesting phenomena that we're still learning about. None of these look tornadic today as such. You want the winds to rotate around the tornado. They're being observed. What you're seeing here is dual pole Doppler radar. And that's what each one of all the National Weather Service sites are dual pole, which means they can see in a two-dimensional view of these rain droplets and they can detect hail very well because of that and all. And because they're Doppler, they can see the rotation as well. So let me know if you have any questions with this.